So good morning, everybody. Let's get started for today's lecture. Remember last time we started studying systems, right? Systems could be in continuous time, defined in continuous time, because if they involve analog or continuous time signals, physical signals, like for instance, audio, voice signal, right? Light, maybe optic light signal, for instance, laser, LiDAR, this LiDAR sensors, they actually sense light waves. What else? It could be, for instance, ECG systems, this electrocardiogram sensors that measure biological signals, right? Electrical signals from the body. So those could be modeled as continuous time signals. Then the processing, remember a system. So let's connect our tablet. A system, so recap, okay? Recap systems. So their goal is, I mean, a few different goals, probably amounts to same thing. They actually model some physical phenomena. Remember, last time I think I just mentioned, let's see, I just mentioned this echo modeling system in communication systems, for instance. You have to model some physical phenomena so that you can, for instance, undo its effects. So actually, you want to, for instance, do inverse system identification, filtering. So actually, maybe these two, the second one was, I was going to say, implement a desired effect on a signal, right? A system implements models or systems, okay, it's plural. So model, implement a desired effect, guys, a desired effect on a signal. So filtering is also an example, right? For instance, we may want to filter a signal so that its high frequencies are eliminated. We will study filters in either time domain, like we're doing now, or in frequency domain later with their frequency response. Now, today we will study impulse response or filtering in time or frequency domain. So implement the desired effect could be, again, filtering actually. Filtering could be, for instance, compression, could be feature extraction, right? So it could be like removing unwanted parts in an image, I mean. So this is actually filter, removing unwanted features or parts or features in a signal. Okay, so compression, feature extraction, you may think of probably many other things. So last time we talked about, remember, LTI systems, linear time invariant systems. These are linearity, so these are some properties actually of systems. So linearity, properties of systems. Remember, linearity means the system, okay, system is something like this, right? We say it's an algorithm. Discrete time signal or continuous time signal goes in this algorithm, manipulates that signal and produces an output. Okay, so produces an output, y of t or y of n. So linearity means this system S, okay, this is my system S, obeys superposition principle. So S obeys superposition principle, meaning, for instance, whether sending signals separately to this signal system, scaling them, or summing them, or taking a superposition of the input signals and sending them to the signal, gives the same result, right? Same result, meaning like at the output, it will be again a superposition of the outputs of individual signals. That's what I'm trying to say. linearity, for instance, we said then time invariance. So it's an important property, right? So time invariance, remember, this also wants this S to not change its behavior over time. So S does not change behavior over time, which is nice, right? For a reliable system. You have a system, you operate it this week, tomorrow you come, you want it the same way, right? Operate the same way as you did before, the same as algorithms. Third property we talked about was causality. Remember, this is important. Causal, from the name implies that the system actually does not look at future values. So output at a, for instance, current time point only depends on all the past input values and the current input value. So it's as the name implies, this is important for real-time implementation or online implementation sometimes. Implementation of systems. Today we will also talk about stability as the fourth property of systems today, later. So I think we've done some examples on these LTI, especially these two are called LTI, right? The other two are independent, of course. So we started with discrete time systems, and we said there is an input-output relationship, right? And actually for LTI systems, we typically define an I/O relation. So remember, LTI systems, actually for these guys, they have a simple input-output relationship, I/O relationship, okay? So for any signal, it's gonna depend on simple relationship, depending on, we will define this actually, impulse response of the system. Well, we will define this, but first, guys, let's rewrite a signal in terms of delta functions. Let's to derive that. So for any signal, okay, for any signal, I have, okay, let's say x of n. Okay, its index is n. Let's say it starts from, okay, 0 at -2 at -1. I have just some values. It will be x of -1 here, of course, right? Let's say it's x of 0 at this point, x of 1, right? 2, x of 2, that's, I mean, it's just, let's say it's 0 everywhere else. I can represent x of n as sums of shifted delta functions. I can represent any signal actually, any discrete time signal. Any discrete time signal, x of n as, let's write this, as sums of these xk values. Okay, these are the xk's, right? So maybe let's write here a generic one, xk, here k equals 4k's, of course. So this is, you see, like the coefficient, xk times delta n minus k. So what is delta n minus k? So recall, so maybe recall, for instance, if I have delta, let's plot delta n minus n0. I think you guys can all imagine this. It will go to integer n0. Of course, n0 is an integer because we are in discrete time world. This is unit 1, right? This is delta n minus n0. It's 0 everywhere else. Okay? This is the simple impulse signal, impulse function. So that's why here I can write, if it's, even if it's an infinite extent signal, right? I can really represent my signal in this way. So this is really, if you open it up, it's really like x0 times delta n. I mean, if you rewrite this, x of 0 times delta n, right? K equals 0, k equals 1, x of 1, delta n minus 1, x of 2, delta n minus 2. Of course, it's gonna go till much larger values. And also it's gonna have the other way around, x of -1 delta n plus 1 plus x of -2 delta n plus 2. And these will also go back to other big case, right? Big negative case. So, I mean, I will have things like x of -1000 delta n plus 1000. Okay? And if it's a large extent signal. So for an LTI system, so let's write this. So xn goes in. So LTI system, okay. So let's see, using its properties, we'll derive something here. So let's say I know y of n, let's say this, the operator was t, y of n is t of x of n, okay? It's an algorithm, right? Mapping an input to an output. So here now, t of x of n, it's written as actually sum of shifted deltas, weighted deltas, k minus infinity to infinity, x of k, delta n minus k, remember, right? Now, because it's an LTI system, actually, you see, this is a superposition of inputs, right? Superposition of inputs. So I can actually, linearity means I can take this t inside, inside the sum, right? So it will be really sum k for all k, t of x of k delta n minus k. This is, by the way, here a coefficient, right, guys? So here I have to actually, let's just write our, let me maybe show it on the next page. So again, continuing with this guy, y of n. Now we said k, the sum, infinite sum is here. Now I have x of k, delta, a t of the delta n minus k. Okay? So also, guys, this is due to time invariance, we will now define something. So, okay, first here at this point, let's define this. We will define something called the impulse response, which is t of delta n. What does this mean? This means take my signal system, okay, my LTI system S. I mean, we said it's S system S, but it has a mathematical operator T. Send an impulse response to it, impulse function to it. The output is the impulse response. This H of n is called the impulse. This is definition, by the way. Define impulse response, let's say. Always think of it as send an input, delta n is input. Then T of delta n, okay, goes out as H of n, which is the impulse response. The important thing is impulse response defines the system completely. Actually, these H will be, we will see later, like our filter coefficients, for instance, okay, filtering system. So now let's say, actually, maybe let's define this H of n here, more formally, H of n, impulse response of an LTI system. LTI system, okay? This is important. Please know this. So now we continue on this side, guys, our derivation. Now I know what is this. If I ask you now, due to time invariance property, here we use linearity, I should say, we use linearity of the system. S, let's say. Now we use here time invariance, okay? Time invariance, because we already started by assuming an LTI system of the LTI system S. So then what do I have? Just what does that mean? If delta n goes in to the system S. H of n goes out. Now I'm telling you delta m minus k goes in, right? Time invariance is this. The same as what goes out? You guys tell me. Just look here, from here to here. It's a time invariant system. So I have at the output what? Shifted, right? Guys, I think some answers are coming probably. Let me look at the chat. Yes, Evren, thank you. H of m minus k. Yes, also Salih. Thank you. Yes, shifted impulse response. So now we have the output. Any questions, guys? K minus infinity to infinity, x of k, h of n minus k then. Okay, using this is using time invariance of the system. Now this is called, guys, convolution operation. We just arrived at the definition of convolution. Okay, this defines this equation actually. Equation defines convolution operation. We say actually y of n is equal to, let's just repeat it. It's an important equation you should know for all your life as a computer engineer. Convolution, because it implements filtering for us, you should really know it by heart very well. We show it by, I mean, you will see this operator a lot also with this probably notation, but of course you should always check what the notation is. This is meaning, so this equation says x of n is convolved with h of n, or we will see its properties now. It's also h of n convolved with x of n. It's commutative. X of n convolved with h of n, the system impulse response, right? So input. So we should say, to again summarize, for an LTI system then, once we know h of n, the impulse response of this system, let's say S, for an LTI system, S, let's say, system S, then we always know x of n goes into, this is my S. Now we should of course always say, hey, I know its parameters. If I know how to model this, or h of n I know. Of course, if you don't know it, there are some systems that try to identify that system function. Those systems are like trying to implement the inverse system for a given system. A little bit more advanced signal processing topics, but for us in this course, mainly, you will have try to figure out the system or the input through some impulse functions I will show you, but it's important to know at this point, given input x of n and h of n, you guys can write the output or calculate the output, of course, as convolution of x with h. Okay, this is important. We'll look at some properties of LTI systems, but let me maybe first look at FIR system and ask you question: is the FIR, let's say, FIR filter or system? I think we've learned this last time. I'm going to repeat. Is this LTI? This was our question last time, I think, to you. I have a question here, but okay, if I didn't ask it last time, guys, do it. But by this question, let's repeat what was an FIR system. Remember, it's actually x of n goes in. Remember, we had actually bk, x of n minus k. Now you guys will see those bk are really, remember, we had filters bk. FIR, filter coefficients, sorry, filter coefficients, right? Filter coefficients BK. Actually, you see these BK form my HK. Maybe let's first, so they will be equivalent actually. Let's first study properties maybe of actually these systems. I think it may be better to study them now. Properties of the convolution, let's do that. This is, you guys do this as an exercise, by the way. Show it. It's a yes. LTI, I mean, so show this. Properties of convolution, okay? This is the operator, remember. This is the convolution operator, notation or symbol. So now I have, okay, it's not. Oh, okay, I can't draw a straight line. All right, so let's say one commutative. We know what commutative means. I can exchange the order of the two inputs to this operator, okay? So this is an operator, let's say, right? Operator, convolution operator. Commutative means take two signals. It could be x1n convolved with x2n. Of course, I know then this is equal to x2n convolved with x1n. We can show this if you want. So let's just see x1 and x2 and minus k. It's really change of variables. Show, for instance, this was k minus infinity to infinity. So just now say this is, let's say m, okay? Now my k is m plus n. Actually, you see, because it's a minus infinity to plus infinity sum, now change of variables, okay, I want to go from m to minus infinity to infinity, which is still fine, right? Because because it's a discrete sum, m normally in this change of variables goes from plus infinity to infinity, but doesn't matter. For the sum, I can really exchange it directly. So for n, I need to write n here actually. Let's write n. N will be k plus m. So I have actually x1, I'm trying to see k plus m, x2 m, right? This is, let me see, from minus infinity to infinity. So let me check actually this, I end up with a negative sign here. Actually, this should be the same as the other one, but I can try to refer this to n minus k. Am I guys correct here? N minus k, right? Guys, I think you guys, of course, we are. Okay, it was x1k, right? I just look at our definition, guys. Xk n minus k, okay. So actually here, I need to go to m. Here, x1k becomes, guys, k becomes, what is k? N minus, right? K is really n minus m, right, guys, from here. Yes, I need to really get exactly the same thing with m. And this is right, x2m. Okay. So actually, this is exactly equal to x2 convolved with x1. I mean, of course, of n, right? And we just showed commutativity. The associativity is very similar. Now, the second property, I mean, this is done. 2 is associative. Okay. Here, guys, it should be really k because k goes from, I mean, the sum goes over k, okay? And then this is the shifted, the other guy gets shifted. We will look at how to calculate convolution through graphical method, and you will see that one of these signals is like a filter that gets flipped and goes over the other signal. So associative property is already, we know, it's a property which shifts the parentheses as we want. So I need three signals, x1, let's say x2, and I will place the parentheses now. For instance, I can place it like this, or I can just shift the parentheses, which is really very handy in many operations. So this would mean the order, right? Or if I have multiple signals to convolve, shifting these parentheses means I change the order of the operation. Here, I first convolve x2 and x3, then convolve them with x1. Here, I do other way around. I convolve x1 and x2 and then convolve with x3. Of course, due to commutativity, I can also convolve x1 and x3, then convolve with x2, but that comes from the commutativity property. You guys should, or if you want, go ahead and read the derivation of this from the book. You can show it like we showed here. By change of variables, writing these convolutions and change of variables. Third property is distributive over addition. Distributive over addition. I have, this is distributive over addition. You guys know, for instance, let's say I have again three signals. Two of them are added, let's say. Okay, I just take x, h1 and h2. This is the operation, meaning two of the signals are being added and then convolved. Okay, this is the operator, remember, we are interested in. This is the standard addition operator over signals. Now pointwise addition, right? Now this would mean, we know, first xn convolves h1, then convolves h2, and you can add them up. Convolve with h1, then also convolve x of n with h2, and then sum them up. Okay, this is distributive over addition. Fourth property, it has an identity element, has an identity element, meaning again this convolution operator. Okay, I mean, these are all properties of convolution operator. This is really, as you may guess, probably delta n. So we should say this is a unit impulse sequence or signal, discrete time signal. So when it's a discrete time signal, I can write it as a sequence or name it as a sequence. This would mean x of n convolved with delta n is x of n itself. You can really see this from the definition, okay? Because remember, this is really how we represent x of n itself. We did this, right? Minus infinity, we said I can really represent any signal as this, and this is already the definition of, this is showing it, x of n convolved with delta n, right? Because I can take all xk values at each time point and multiply it or represent it as a weight for a delta function, shifted delta function to that point, then it's a really, you see, equivalent to the whole thing. When you sum it over, it's equivalent to the convolution. Then, for instance, I can at this point ask you question, what would be x of n convolved with delta n minus 1? So maybe let's do this. K, x of k, okay, x of k delta of n minus 1 minus k. This was x of n, right? Guys, this is, okay, I have to again make sure I'm writing this correctly. This is x of n. I mean x of n, of course, because x of n delta n is also already x of n itself. I was trying to show it's x of n. It was fine before, don't worry. This was also fine, but this is already x of n. So sure, it should stay as x of n. This is what I was trying to show. Here it's the same. Now this guy really you see, shifts the signal x of n by 1. You can view this as, this will be only non-zero at one place, right? This was only non-zero when n is k, right? Similarly, here, or k is n, here this is really when non-zero only when k is n minus 1. So you can think of it in that way too. This is really, you see, taking a signal, and we know actually this is also something you can now think of. If the impulse response of a system h of n is delta n minus 1, I know this is a delay system, delay by 1 system, for instance. Y of n is really, this implies this actually. And this is a delay system by 1 sample. Is that fine? Is this clear, guys? And we can actually maybe write this as 5, the delay system actually, delta n minus n0 convolving x of n. This is a property. Again, it creates a delay on the input signal. Okay, so let's say delay. So delay system, impulse response, delay by n0 is delta n minus n0, okay? This is equal to its h of n. So this defines, we said, x of n goes in, h of n is equal to delta n minus n0, okay? And I have now, you see my output is really the delayed version of the, so this is the delayed input. Intuitive, right? Quite intuitive. We also have, this is, we said this is our impulse response. Okay. We also can define a step response. Typically, I mean, almost always this is used. But we can also define, okay, let's define a step sequence. I think we've defined this last time, but let me recall. And then we define a step response, okay? So this is really u of n, okay, is 1 for n greater equal to 0, 0 for n less than 0. It's really this guy, remember. It goes on actually. And it's like as ones on this other side, u of n. On the positive side, I mean, and then it goes as zeros on the negative side of the axis, okay? I think it's clear, right? It's a very basic sequence, intuitive. It tries to, you see, zero out some parts of the signal. So it starts the signal actually at some point when it multiplies another signal. So we can write this guy, by the way. From here, you can see really u of n is delta n plus delta n minus 1. I'm writing what I'm seeing at this plot actually. Plus delta n minus 2, right? This goes on. So we can really write it as sum. Let's write it both ways. Delta k0, so I can just write this first, delta n minus k shifted, and it goes from k0 to infinity, right? So this is one way to represent the step sequence. So you see it's a sum of deltas, shifted deltas, starting at some point. We can also rewrite it by a change of variables. We can rewrite this as, just to know actually, another, maybe let's write from here, another representation is u of n. Just do a change of variables. If I just say L is n minus k, this guy this time will go from L minus infinity to n. Change of variables, L is n minus k. Okay? Just to know, you may see it maybe either goes from minus infinity to n delta L in this case, or it's just sum of shifted impulses from k0 to infinity. Now, step response is defined, step response of a system. This was impulse response of an LTI system, okay? Now, step response again of an LTI system. This time, remember in the impulse response, as the name implies, impulse goes in. Now, a step goes in, U. So it will be really, let's say the system as LTI, the step sequence goes in, and typically we call the output as step response S of n, okay? I mean, this is of course the output, right? Y of n, and here X of n was really U of n, right? Set the input, so set the input to a step sequence. Input to a step sequence, okay? That's it. So let's see. Yeah, I think we can do this derivation. We can write U of n. Okay, it was again going to this LTI system S. This is LTI. Okay, LTI system. Maybe let's write LTI outside. And let's say this is Y of n or S of n. Now, step. Now, U of n, we can write it as, let's see, which one? We can use this first one, 0 to infinity. 1. 0, U of n is really k0 to infinity delta, shifted delta, right? This goes to the step response S. I mean, to the system S. Don't get confused. This S is little s. This is LTI system S. They are different things. Okay, so now I know actually this is equal to my output, right? And this is really, I know that equivalent to the whatever the impulse response of the system is convolved with U of n. So it also has an impulse response. I know this always holds, right? This is always holding. So now we will write again Y of n is H of n convolved with X of n. This is X of n, which is equal to this, of course, U of n, X of n, which is equal to, now let's write X of n as these infinite sum of delta functions. So from here, Y of n is H of n convolved with this guy, 0 to infinity, okay, delta n minus k. Now let's use these LTI properties here. And distributive, or actually properties of convolution here is enough. Distributive over addition, right? So I can really take H in. So this will be really k0 to infinity, H of n convolved with delta n minus k, right? Using distribution over addition property. Over addition, right? Because of the property here, we could write this. Now, what is this, guys? H of n convolved with a shifted impulse. We've done this before. Delta, when it convolves a signal, it shifts it, right? So this is really H of n minus k. So in the end, the step response actually from here, step response, this is really some mathematical system manipulations you can do. Step response S of n, or its equivalently Y of n here, is really k0 to infinity H of n minus k. Okay? By the way, this infinity should be nicer. Okay. So you see, it's really integrating the impulse response. Okay? So maybe we could do one example at this point, solve an example together. Maybe let's do it on a new page. Example. So given step response, for instance, response S of n, how can I calculate H of n, the impulse response? We always think about the properties here, the linearity, time invariance properties of the convolution. So here, what is given? We are given this U of n goes in to system S, S of n goes out, right? Now, what is U of n? Or how can I write actually, maybe here, my goal is actually to find this. The question is this, right? Question asks us this. Delta n goes in S, what is H of n? This is the question. So I should be able to write delta in terms of use here, to be able to use superposition, for instance. So here an idea is, so let's say write delta n in terms of U of n, okay? So actually you can see delta n is U of n minus shifted U of n minus 1. So maybe note here, just imagine you have U of n, it's going on here, U of n, and 0, 1, 2, 3, and it's all zeros here, right? Now, what is U of n minus 1? It's really one shifted version of this guy. It's gonna start, now it's 0 here, 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 it's all zeros, but now it starts here. Right? So actually, maybe let's put these in red so you see the difference. This was U of n going on. Here now U of n starts at 1 and it's 0 at this point. Take the difference. So delta n is really when you subtract from U of n, it's one shifted version. So I know delta of n is U of n minus U of n minus 1. So from here, we can use the property of the system. U of n minus 1. So let's just do U of n minus 1 goes in, S of n minus 1 goes out, right? Because it's a time invariant system. So now just subtract the two results. Through superposition, we should say, then delta n goes in S, then I have H of n equal to S of n minus S of n minus 1. Use superposition, okay, of inputs. I mean, because here this is really U of n minus U of n minus 1. So I just brought their two outputs and sum them up. Of course, there is a negative sign there. Use superposition of inputs. Linearity also, right? Linearity. We use time invariance. We use this was time invariance property. Now we use linearity properties. Okay. That's good. I think I wanted to note one more thing. If delta is convolved with itself, before we go, let's note this also for your notes. I just, maybe you may get confused. Don't get, I mean, what is this? You may see this delta convolved with its shifted version. Remember, this is an identity element. Actually, this is itself. Okay, n minus n 0. But if I have done, for instance, now this was shifted by another, I mean, this is another signal, right? A delta shifted by n1. It's convolved with delta shifted by n0. What is then the result? Because this is, remember, or this one, doesn't matter, whichever, is like the impulse response of a delay system. The result will be delayed, right, by both of them. This is the result. You should please note this. Okay, don't get confused. I mean, when you see two shifted impulses convolving each other, the result will be delayed by the addition of the shift amounts of the two. Okay, another property you can say, or not another. I mean, it can be derived from others, but property of convolution. This is important also to note. Okay. Then I think we can do, did we do cascaded and parallel systems next time? I think we did not. Okay, we will do cascaded systems, parallel systems, and we will also do a calculation of the convolution. I think that would be nice to do that. But let's give a break. Actually, I realized because our faculty said let's do 40 minutes lectures. I always do 50 or 1 hour lectures. Let's don't be too hard on ourselves and let's give a break. Do you have any questions, guys? All right, so let me stop the recording, pause the. All right. If most of us are back from the break, let's continue where we left off last time, right? All right. Just a sec. I want to. Okay, guys. All right. So I think we were, okay, we did this example last time. Now I want us to do a computation of convolution example, okay? So let's do this. So computation of convolution. Okay. So for instance, this means it means is given an x of n, an input signal, an input, and the h of n, the impulse response. Okay. We want to compute, this is what I mean, this is equivalent to this actually, let's say computation of convolution. This is what we're doing, compute YFN. Okay, so this is what we want. So let me give an example now, example, two signals or a signal and an impulse response, but it's a finite impulse response and it says just a set of coefficients, right? So I can also represent it similarly on a graph. I mean, even if it's infinite extent, if it has a rule, we can show it, right? On a graph, of course. So let's say the thing, okay, I'm trying to show was x of k is this 2, okay, it's 2 here, 4 at 1. Maybe I should have, okay, anyways, I mean, it's not up to scale, you guys can see that. It's 1 at 2 and it's then 0 at 3. Then it's of course continues to be 0 and it was 0 at -1 and -2. Let's say, so actually x of n is really 2 delta n plus 4 delta n minus 1 plus 1, right? This is delta n minus 2. Of course, you can do this as convolution of delta functions, but let's do it with something called the graphical method first, and then we can do it the other way around. So h, let's say, is given by 3 and 1. So these are now this is h. It's 1, it's so 3. It's 3 at 0. Sorry. All right, it's 3 at 0 and it's 1 at, okay, it's not up to, it's not to scale actually. So let's see for, okay, so somewhere here and here, 0, 1. Okay, so guys, I will Now I'm trying to see which way I should start with. Okay, let's start with the, yeah. Let's start with this methods of shifting and multiplying and okay, all right. So guys, this is it. Let's say I will bring, okay, what we will be computing will be this. We will be computing, let's say it's this, not let's say, but it's actually y of n, right? Which is equal to convolution of, so what I have is here, this one, x of n goes into a system with h of n, and what is at the output is really x of n convolved with h of n. Okay, so this is y of n. Okay, so this is h, the definition of convolution is h of k, x of n minus k. K from minus infinity to infinity. Okay, now, guys, let's try to implement this. For instance, for n equals 0, or I mean, for instance, y of 0, I would really have another sum, k minus infinity to infinity, h of k, x of minus k, right? For instance, for y of 1, I would have, again, k from minus infinity to infinity, h of k, x of 1 minus k. So I want to now plot these, signals on a graph and then do this multiplication on the graph and sum it up, integrate the graph. That's what I want to do. So h of k, bring h of k here. I could have done it the other way around, but anyways, here I'm shifting x on top of it. Okay, it's fine. H of k is itself, but now with just k here. 3 and 1, 0, 1. Okay, so I have x of minus k. Now I bring that signal on here as a graph, right? It will be graph multiplication, or graph meaning not the graph in the computer science, but it's a plot of functions, graphing of the functions. H of k, x of minus k will be flip the signal, right? So it's gonna be really 2, 4, 1, and then you have these zeros. Okay, now let's just, I hope you guys are seeing these graphs. Okay, so now let's just do the multiplication, which is, I mean, I'm carrying out the convolution operation here, right? Which is h of k, x of minus k, and then we will sum that plot actually, or graph of the function. Do the multiplication, it's gonna be 6 here. And it's going to be everywhere else 0, right? So I should just say this is the graph, or I mean the multiplication of the two graphs. Then I have actually now sum it up. Now sum it up over all k. This hk minus, I mean x of minus k. This is really 6, right? Now this is showing me y of n equals 0. So what I'm trying to show here is the filtering idea. We flipped one of the signals. Here you can say, hey, H was the filter, but we flipped X, which is fine. X, let's say, was the filter, H is the input. We can do, because it's commutative, we can do the same thing other way around. But we flipped one of the signals, here X, and now we will be shifting the signal over the other signal. So you see here, flipped filter, okay? So let's not, this flipped filter, okay, let's write it here, flipped filter. Now we will start sliding this. Now slide this flipped filter over the other signal. I mean, flipped signal, you can say, over the other signal. to get the other time points, calculate the other time points, other signal. Okay, so now let's do that. For instance, n equals 1. Now I have, let's again plot everybody, guys. H of k stays as it is. So I'll bring it again, right? Just bring h of k. It was 3 and 1. Just bring it here. Let's say it was 3 and 1 at 0, 1, and it was 0 everywhere else. Okay. Now I have to bring x of one minus k, meaning that filter has shifted one to the right. X of 1 minus k. I'm calling x the filter now. It's fine. So you see that flipped filter there shifted by 1 to the right because it was x of minus k. Now it's x of 1 minus k. Okay, it will be 2, 4, 1. 2, 4, 1. Okay, I hope you guys see this. Maybe I should use red here. The same with here, the reds. Now do the math. Minus 2. Everybody else is 0. Now do the math. Multiply the 2. What is it? I have really 12 here. Okay, it's not going to be... okay, let's plot it here so that... K, guys, because I want to show the full extent, it's going to be x of 1 minus k times h of k. I have a 12, right? Doing a pointwise multiplication here, 2, and everything else is 0 again, right? Exactly. So actually, guys, in the end, we have to integrate this function. This function, we have to integrate this. You see, this was again the filter that is shifting. This is, you see, the filter shifts towards here. Starts, flips itself and shifts over towards positive k, positive side of the k-axis. Filter shifts, and then now sum it up, integrate or sum or in continuous time, it's going to be integrate, sum over here, over k, yeah, and then that is really, generally it's going to be like this, right? H of k, x of n minus k. In this case, for n equals 1, this result is 14. We can do this. We can, I mean, continue doing this. Let's do it for n equals 2, 2. Let's, I hope you guys are following. HK again. This is good exercise for you also to understand the mechanics of convolution. That's why I'm doing this actually. For discrete time especially, you can probably say I can do this in an easier way. Just apply the formula, but just a sec. I think, guys, there was a bug in the, okay, maybe, okay, a fly. All right, 0, 1. Now let's bring R, x of 2 minus k, 1 shifted. Okay. One, 4, 2. Okay. And it's all of these are 0 everywhere else. Actually, you may be hearing the noise. Okay. Let me just a sec, guys. All right. So now do the same math here. X of 2 minus k now. You see our filter shifted, right, by 1 to this side. This was 0, 1, 2. Now do the multiplication again. This is how you do convolution, actually, exactly here. Now h of k, x of 2 minus k, it's 3, right? 3 times 1. 1 times 4 is 4. And I have zeros everywhere else. Okay, so just sum this up. For instance, I know from here, this was y of 1. Now y of 2 is 7, for instance. Should I continue? You can see it this way. N equals 3, yes, I will have one final overlap. Then I won't have any more overlaps, right? Filter shift. So let's do that too. So, okay, y of 2 is 7. Let's write it here. Y of 2 from here, you guys can see it, I think, is 7, which is 3 plus 4, of course. Now let's do the last one, because after that, there won't be any more shifts and everything else will be 0. So n equals 3 is really k. Here, h of k, 1, 0, 1. Now x of 3 minus k, right? Just bring the filter here. There will be a 1 here, and everybody else here is 0, of course. And then there will be 4 and 2 here. 4 and 2. So now do the math. Just overlap, right? I mean, just multiply them from here and sum it up. Y of 3 is equal to 1, of course. I hope you can see that, right? I mean, just for your notes, we could have written, okay, let's maybe just complete the graph because this multiplication graph really is 1 here and it's zeros everywhere else. So it's really 1. So this is really h of k, x of 3 minus k. Now y of 3 is 1. Okay? From here. It's the sum of all these guys. Okay. So then the result will be, let's write this, y of n. We found it already actually. We found 6 for y of 0. Y of 0 was 6 here. We found y of 1. Where is it, guys? Here, y of 1 was 14. Y of 2 is 7, right? And y of 3 is 1. So in the end, our y of n signal, I mean, n k doesn't matter, but we used k as the dummy variable for the result, let's say, for the convolution sum. It was 6, 14, and it's not to scale, right? Just, it should be fine, 0, 1, 2, and it was 1 for the 3. And then it's zeros everywhere else. There could be questions. I'm going to check. If you have questions, please ask. This is our y. It becomes, you see, 0 afterwards 4, and for n greater than equal to 4, it is 0, and also it's 0 less than, when n is less than 0. Yes, Mustafa, great question. We would arrive at the same result if we flip the other graph, meaning if we looked at x of k times h of n minus k. We would get, let's note this, due to convolution property of commutativity, due to or commutativity of convolution, let's say, T of convolution, we would arrive at the same result, meaning if we worked with, guys, worked with in this case, x of k, h of n minus k. Okay, so meaning we shifted x of k. Good question. Yes. So this is how you would really do the convolution. Okay, so it's just for your notes. Okay, make it nicer. I mean, for discrete time signals, if the number of non-zero elements are this small, another easy way would be write both of them as delta functions. For instance, another way for discrete time convolution, of course, is use the delta convolution, right? Another way for discrete time convolution, you can't do this, however, for continuous time. You would have to do this graph shifting and integration. Another way for this is important, discrete time convolution. Remember, we've written x of n, let's take it, 2 delta n plus 4 delta n minus 1 plus delta n minus 2, right? And I need to also write h of n. I think it was 3 delta n plus delta n minus 1. Let's just check. Exactly, that's 3 delta. You see, I'm just writing h of n and delta x of n. So this is really 3 delta n plus delta n minus 1. Now you do the convolution. So it's really, actually, maybe let's write the convolution. X of n is this, convolve with, I mean, these are, of course, I mean, you see what I'm saying. This is really x of n convolve with h of n. Now you would have to do all these separate convolutions, right? Use distributive over addition property of convolution. So for instance, let's say take this, convolve it with each of these, and similarly take this and convolve it with each of them. Okay, the same for with this guy. So then I would really have 3 delta n. Actually, this could be a good exercise for you, but let me do a little bit. I would just do 6 delta n, for instance, plus 12 delta n minus 1, right? Plus 3. This is already identity element, so you just have to incorporate the scale 3. Now here it's a shift, right? Plus 2 delta n minus 1, introduce a shift on this left signal, 2n minus 1 plus 4 delta n minus 2 plus delta n minus 3. I mean, it may not be too efficient all the time, but this time it's short signals. So you see now this guy and this guy can be added. It's really 6 delta n plus 14 delta n minus 1, 3 and 4 delta n minus 2 is 7 delta n minus 2, right? Plus delta n minus 3. This is exactly the same result, right? The same result as in this above graph, as in the first way. Okay, first way of convolution we studied, which was by we could say using a graph method. Okay, is it clear? I think this should be fine for now. Okay. Now I want us, or any questions, just ask them. Okay. Clear, right? This convolution operation is important. So let's say, give the title red box here. Okay. All right. So now I want us to look at these cascaded LTI systems and parallel LTI systems, meaning now I have multiple systems. I want to combine them somehow in different ways, because I want to obtain different properties or different effects from the filters. So then that brings us to cascaded connection and parallel connections of LTI systems. This cascade is actually series connection, probably from your circuits courses, or also even from your algorithms. I mean, this is really affecting from mathematics an operation serially, like first do something, then do something, right? So for instance, here it's really like first have the effect operate or execute the effect of S1 on the system, get an intermediate result. Okay, now pass it through another system, that output, get an output Y of n. And what we are wondering here is what is the overall system actually. This is a cascaded LTI, and both are LTI, of course, as the name implies here. We assumed both are LTI systems, and we are wondering what is the overall system. So this is really like equivalent to, there is an equivalent overall system, okay? S overall. What is the equivalent overall system? So question is, what is the equivalent overall system, okay? All right, so let's look. So let's just say Y of n is, remember the properties of the convolution. Here you would be like saying, hey, I have really x of n convolving. Let's say this was h1 of n. The impulse response for this first guy was, let's call it h1n, this guy h2n, and I'm really looking for h overall n, okay? So x of n convolved with h1n, and then this was my wn, right? And this was getting convolved with h2n. Now I will use first commutative property. So let's maybe plot or say this was wn, right? Commutative property to exchange the order of these two guys. I have h2n convolved with h1n and x of n, right? I can do this. Now I can move the parentheses. Now this is commutative property we've used here. Okay, so going from this equation to this equation, now use the associative property of convolution. Now I'm going to the next equality. I would say I'm moving my parentheses freely, like changing the order of the computation. First, convolve the two impulse functions, then execute their final overall effect on my x of n. And this is really, you see, nice result. Hey, I have my overall impulse response really being equal to, and I can do a commutativity, right? The order of this operation doesn't matter. So it's really H1 convolved with H2. All right. So this is the overall system. Impulse response for cascaded connection. For cascaded or in series connection of systems. And this is connection of LTI systems. This I think you guys can see it immediately right away. Extendable to many filters or many systems. So for n systems like this, for instance, n LTI systems, valid, it's valid. Valid for, meaning I have S1, S2, Sn, and with all their H1, H2, right, the impulse responses, the overall system, what is I can ask you, what is your guess? I mean, it's already, I said, a straightforward extension. The x of n going to H overall equivalent system, right? And y of n, what is H overall, the overall system, I mean? convolution of all these impulse responses, right? So it's really gonna be H1 and convolve with dot, dot, dot. Everybody convolves each other. This is the overall impulse response. Valid for, so extended to multiple number of systems, okay? Not just two. This is valid for cascaded LTI systems. Now, let's look at parallel connection of LTI systems. Okay, so this will be, now there are two parallel, S1, let's say first. There is an S1 with its own H1. There is an S2, and as the name implies, they will be connected in parallel, meaning, guys, I'm this time trying to submit or send my input to these two systems separately. So I want to then add the outputs. Okay, this gives me a new system, actually, this connection. This also was giving me a new system. I'm trying to get a new effect. We will study these particularly in frequency response topic next time, after we do the continuous time systems, by the way, in time domain. We will see that, for instance, by combining two low pass filters, let's say, maybe they are not that good quality. We will see what that means. I can get a better low pass filter, for instance, or I can try to get a band pass filter by doing this connection, for instance. Okay, we will see what that means. Don't worry. So here now the overall filter or system, I sometimes use it exchangeably, you see, which is fine. Let's say it's gonna have an H. So overall system is, let's say, S. Okay, I got two systems. I'm connecting them in parallel. What is the, now I'm asking, what is H of N? In terms of H1 and H2, of course. H1 and H2, okay? So let's just do the math here. What is Y of N? We will again use properties of the convolution operator. X of N convolved with H1N, right? Plus, right? I mean, here there is an output here, W1, W2, let's say this is really W1, and now W2N is also X of N, convolved with H2N, right? This was W2N. Now you can see again from the distribution over addition property, I can re-express this as the addition of the two, I mean, X of N convolving addition of the two impulse responses, you see. Now that's the overall H of N, right? It's really, you see, in the end, the overall system is really X of N convolved with addition of the two impulse response systems, impulse responses of the two systems. So H of N is really, we've seen, maybe don't write it here because it's in my equation. Okay, so overall system here has, in parallel connection, has this impulse response, which is H1N plus H2N plus, please pay attention to the plus. But for cascaded, let's just recap. For cascaded connection has the impulse response, H of N. We've seen it, right? Just before this time it was convolution. Just pay attention, okay? This is different. This is convolution operator, this is addition operator. Okay? Any questions here? And also, guys, for the N systems, it's the same. Extension to N systems is the same. Here. So I would have really X of N, just S1, or maybe let's write it both here. Extension to N systems, X of N, S1. Okay. All right. S2 dot dot Sn. Maybe add them up all here. Dot dot dot. Of course, they all get added up here to give me a y of n. And our goal was to be able to express this overall equivalent system, right? Which is this big system S, and X of n goes in and y of n goes out. And it's the same as before, H1, H2, Hn. Now it's going to be addition of. So remember, H of n now, of course, I can write it as the sum, right? I mean, H1, H2, H2. Same, maybe this is parallel. So it's parallel system. Let's write for the nodes cascade system here. Parallel connected system. But, well, what is happening here? Okay, all right. So my parallel cascaded system is here. We've done it, but let's just do S1, S2. You know, the output of the first system goes to the second, that one goes to third, and then the last one goes to Sn, and I have y of n. And here our goal was again to be able to express this whole system, right? So it's really again X of n going to this big system S, y of n going out. And in this case, remember, this was addition here, let's say parallel system. Overall impulse response was addition of each impulse response, or all impulse responses, let's say. I won't say on top of each other, but all pulse responses. Now here, it's the convolution of all. So H1 and convolved with H2 and convolved with HNN, right? So now for cascaded system, this H of n is really convolution of all impulse responses, okay? I think this should be fine. Any questions, guys? But I mean, is there any way to show it? You can't probably here some, because I'm thinking now, no, everyone. I mean, you have to show it in this way. You can check, but as far as I know, I can't really show it. Can you think of a way? Because it's not sum. Sum is already like the addition operation. So, I mean, no. Okay, thanks for asking. All right. So, for instance, I can ask you this now. Oh, are we done with it already? Okay. When did we start, by the way? I think it's time for a break probably, because we started at 10:40. We could give a 10-minute break and start 10:30. Then I will hand you over to your assistants at around 11:10. Or let's maybe do one example just to ask you. I'm drawing a different, just combining both series connection or cascade connection and parallel connections. I'm connecting these three systems in this way, guys, with their own, of course, H impulse responses here. So I'm asking you, what is the overall system response here, or impulse response? I mean, what is H of n? Okay, the overall H of n. Can you guess it now just by looking at this plot? This is the question. Let's see, any answers? Yes, thank you. H1 convolved H2 plus H3, right? I hope, please guys, check yourselves. It's already from the properties H1 convolved with H2, right? That completes the upper branch, top branch. That's the equivalent system for the top branch. Now, add these guys with H3. Thank you. Yes, I think it should be probably clear for most of you. Okay, we could give a break. By the way, is any of our assistants here? Want to talk to him about the quiz? But okay, I will talk to them in the break. All right. So see you after the break. Maybe it's 10:22 now. Let's make it at 10:35. Okay, let's get back together at 10:35. So I think we've left off where we studied cascaded and parallel systems, right? And we can think of many different configurations, actually. I asked you one just before the break. All right, this one. And you can think of many different variations, right? I can see here, right? You can think of many different combinations like this. And calculate their overall system response. Okay. So maybe we could define now also stability. Before we go to another property of systems, before we go to that, recall, we said causality. We talked about causality of a system. And we said, we defined it by saying the current output doesn't depend on the future inputs, right? General definition was this one. So general definition was, let's write it actually, definition. A system is causal if the output y of n, if the output y of n only depends on, here only is important, only depends on current and past values of x of n, current and past values of x of n, okay? So example, I think, remember we gave some examples before. This is another one. For instance, I'm giving you this system now. Is this causal or not? My question. This is IO relation, right? I'm giving you IO relation of a system. I'm asking you, is this system causal? Just to recap from your previous knowledge. What do you think, guys? Some of you answered, I think. Let's check. Yes, thanks, Evran. Yes, it's causal, right? Because just check a few values, for instance. Yes, it's causal. I mean, I could just, if I were you, for instance, just y2 is x of 2. I mean, it's a similar rule, right? And it's going to be x of 1 squared. So it's really to calculate my output at time 2, I'm looking at the input at time 2 and input at time 1. Yes, it's causal. Now, checking causality for causal LTI systems, we have another way. Causality for LTI. This was general definition, by the way. For LTI systems, we can check the impulse response. Check the impulse response, and if it has certain constraints, you can say it's a causal system. So recall, for a LTI system, I can write h of y of n is h of k, x of n minus k, right? So imagine for k positive, right? This actually for k greater or equal to 0, this really gives me what I want, meaning for y of n, right? For y of n, any y of n, let's say, for k greater than 0, y of n depends only on x of n and x of n minus k. So these are past values, which is fine. So this would be causal. But for k less than 0, if k was a negative number, right here, so that is the filter coefficients for in the negative axis, then I would need x of n plus k, right? I mean, I could maybe say k prime here. I mean, this would mean if k is 0, k is negative, I mean. So this would mean I'm looking at future values, right? These are the future shifts. So this gives me future values of x of n. So that would give me now a definition for LTI systems for causality. Definition of causality for LTI systems. LTI systems now, you see specific case. An LTI system is causal. System is causal. We should say if and only if and only if, this means both ways, right? H of n or k doesn't matter here. For h of k is 0 for k less than 0 or n less than 0, h of n, right? So this is then actually a specific condition for causality for LTI systems. By the way, guys, we've been talking about FIR, finite impulse response systems, right? With this finite number of coefficients. Maybe, let me see, I think every year I mention it a little bit. I know it's, I say this is not something that you are responsible for. Let me see, but recall, let's just to recall the difference equations. This is, I think, good to know. Recall difference equations, general system of linear coefficient, constant linear coefficient difference equations. These are actually difference equations. These are an important class of difference equations. These are an important class of LTI systems, by the way. Okay, important class of LTI systems. Okay, so difference equations were, remember this, AK y of n minus k, k again from minus infinity to infinity. Remember, we had recursive computation. The IO relation of the system, depends also on shifted versions of the output itself. That brings the recursivity. But for us in this course, we were only working with k equals 0, AK or A0 equals 1, remember. For us, actually not k minus to infinity. Let me see, guys. I just automatically I wrote this, but these should be really k0 to n, and this should be, remember, k0 to m, the filter finite, because I'm saying already finite impulse response systems. This is the one. So remember, so n equals 1, right? Oh no, 0, man, of course, 0. 0 because I just need A0. A1 would bring the first shift. A0 equals 1, which would bring us to y of n is k0 to m bk x of n minus k. Remember, this is the FIR case. This is my FIR system, finite impulse response system. Remember, this is actually, if you guys recall, my HK, pulse response system. Finite, really finite, because I have finite number of BK or HK, or have finite number of coefficients, okay? But there could be systems, I mean, here. So, okay, FIR system example, maybe I should give. For instance, y of n is 1 over 2 x of n minus, oh, what happens? Oh, sorry, minus 3 over 2 x of n minus 1, right? Let's see, it's just this actually. And from here, you guys can tell me the filter coefficients. So, for instance, you would say, hey, B0 is 1 over 2, B1 is minus 3 over 2, BK, right? Or H of 0 and H of 1. Equivalently, this is H of 0, this is H of 1, right? The filter coefficients. But extra information just for you, because to know this, there are infinite impulse response systems. I was telling you, this is more in the realm of electrical electronics engineers and a little bit more advanced signal processing. So that's why we don't study it in this course, and you really actually typically do not need this. You work with finite number of filters, but it's good to know it as a general knowledge. If I had, let's say, guys, y of n, so I was talking about this recursivity, right? Now you see my IO relation has a shifted output itself here, okay? So let's say I had this relation. So from here, how do I find h of n? Let's write y of n is 1 over 2 y of n minus 1 plus x of n. So my question is, find impulse response. So let x of n, when you find impulse response, remember you let x of n delta n. We did the same here actually, right? Delta n, put delta n. So here, when you let x of n delta n, you found h of n, remember? Which was equal to 1 over 2 delta n minus 1 minus 3 over 2 delta n minus 1, right? That's why we find h of 0 and h of 1. Now here, let x of n delta of n, guys, system here, there is an assumption. You have to really start the system somewhere. So you have to make that, otherwise it's an infinite recursion. So you say system is at rest. So meaning h of minus 1 equals 0, okay? And that makes y of minus 1 also 0. So then you start iterating. So you would say h of 0, now I know system starts from 0, okay? Now h of 0, now insert here the equation, x of n is delta n, right? And y of minus 1 is 0, so I have x of n is delta n, it's already 1, which is x of 0, let's say. So this would be 1, okay, good. Now this is h of minus 1, okay? H of 1, just continue in this way. 1 over 2, now I have y of 0 right here, which this is y of 0, by the way, right? Which is 1, plus x of n, now it becomes 0, because this was delta n, right? X of 1, this is 0. I mean, it may get a little bit confusing, but this is 1 over 2. Now let's do, I mean, you may think it's confusing, but it's not. You will see what I'm coming to here. This will be 1 over h of 1. This was h of 0, by the way, or y of, it doesn't matter, plus x of 2, which is equal to 1 over 4. If you continue in this way, you will see this has this exponential relation, and it starts at 0. So you see I can bring u of n So that would be, you see, this is the impulse response for an infinite impulse response system. You can plot this guy and see that it's really infinite because it starts at 0. It was 0 here. Now starts at 1. Now it has this exponential decay form, right? 1/2 here at 1. At 2, you have 1/4. And it's going to continue in this way. Okay? So you see it's infinite extent. Let me see. Okay. So I wanted us just to note this. So there are impulse responses like this you may come across. That was the idea here. So this is an infinite impulse response. And an example, infinite IIR, example IIR filter is this guy. And here it was an example FIR filter I given. Okay. The reason I gave this, for instance, I can check causality and things like that. For instance, we can check causality of this system. I'm sorry. Okay, I'm fine at the right place. All right. So for instance, example, is this LTI system? They can also, of course, they are a subclass of LTI system. So is this LTI system causal? I'm giving this IIR. I mean, this is, you can just think of a mathematical expression of actually a class of IIR systems or impulse response systems that exist. Now I want us, because it's LTI, remember, we had a definition of causality here at the bottom of the page. You can directly, if you have the impulse response available, because it's an LTI system, I know I can represent this system by an impulse response H, and then I can check whether it's 0 before n less than 0. So check whether H of n is 0 for n less than 0. And it is here for this one satisfied, right? So for instance, this is n. So this IIR filter is causal, for instance. I mean, already U of n tells that actually. For instance, this is just an example. Let me see if we had others. Before that, I wanted, I think, us to define stability before we do a few more examples. And then we will move to continuous time systems. But let's see if today we have the time. We may have to go next time. Okay, so now let's define stability of systems. Another, I think it's the fourth property we are seeing. Fourth property of systems. Systems we are seeing is stability. Okay, and there are different definitions of stability in mathematics. Guys, it could be robustness of a system in general also. Maybe you heard this, an algorithm, right? For an algorithm or for a function, for a system, if you perturb the input a little bit, the output should be perturbed a little bit too. But I'm not talking about that here. Here, this definition of stability is also another important one. This is called bounded input, bounded output. This is, guys, this is called BIBO, equivalently BIBO, bounded input, bounded output. Stability, important, another important stability definition for systems. The first just I mentioned is actually another general mathematical stability, robustness against perturbations. Maybe you heard this of an algorithm, for instance, against perturbations, right? This is also another general definition, but here I'm defining by BIBO stability. This is a specific case. As the name implies, bounded inputs produce bounded outputs. This is very important because the systems may break actually if the system is not a stable system. So this would mean that, guys, let's do the definition. System is stable, the same for the algorithms, right? Typically, we get NaNs, right? Not a numbers in our codes. That's exactly this. We are providing bounded inputs, so finite inputs, and our system or algorithm produces an infinite output, typically, right? That's a problem, not a number. It becomes a number that is not representable in our system, in our digital environment. Then actually you are breaking this BIBO or bounded input, bounded output stability. We try to detect those in our algorithms and avoid those, right? The same idea. System is stable if and only if every bounded input produces a bounded output. Every bounded input produces a bounded output, okay? So in mathematical terms, this is the definition. Also in mathematical terms, just let, if for instance, x of n, this is also, we will see, valid for continuous time systems, is less than or equal to some constant m of x, which is a finite number. Then we should say, then you see, if then y of n is also bounded by another constant, doesn't have to be the same. Okay, this is the mathematical definition. This really tells us something like this. I mean, if these were also valid for continuous, by the way, guys, in absolute value, so y of t is also valid. So I'll just draw a continuous signal just for the sake of easiness here. Let's say, for instance, I have a signal like this, x of t. Okay, probably it's bounded like this. I mean, it should be the absolute value. So whichever is larger in the positive or negative axis here, you get that as mx. You find an mx value. Now, BIBO stability or BIBO, bounded input, bounded output, says that my y of t or y of n doesn't matter, t. Okay, x of t here, of course, this was t. Means t, y of t, the same for x of n, y of n, this is the generic definition. So let's say now it is bounded by my minus my. So it's something like this, okay? So it's really meaning it's really staying finite as a finite signal and bounded by, for infinitely long extent, it's bounded by some constant. This is important to know for your algorithms and the systems you design. Also, a specific definition is, if the system is LTI, we have a more specific definition for the stability. If the system is LTI, this is valid for signals and systems. Stability can be defined in terms of the impulse response, again, like we did in causality. Stability is defined in terms of the impulse response. Okay, so we will have, again, start with the definition I will make again, but let's say, let x of n less equal mx as finite constant, a finite number. It's bounded by, I mean, right, either from positive or negative axis, it's bounded by a maximum finite number. Now let's look at y of n. Let's write y of n. What is the definition? It's an LTI. Once you see LTI, you say, hey, I can write the output of this system. Again, this is really x of n goes to system S and y of n goes out, and we're talking about stability of S, right? And it will be defined in terms of h of n. So y of n, remember, is h of k, x of n minus k, right? So k, I mean, k could be from minus infinity to infinity, or if it's a finite impulse response, but x could be infinite extent also. But it's a multiplication. It's going to be a finite sum, of course. Now let's take the absolute value. I'm trying to apply this bounded input, bounded output idea, and I'm trying to see how is this bounded. Okay, I know from this product rule of the absolute value and sum of actually sum, the absolute value of sum, right, is less equal to sum of absolute value of those terms. I know this. This is well known. H of k, x of n minus k. I can go, remember, one further. This is less equal to, I mean, some stays here, but the product, absolute value of the product is always less than or equal to, remember, absolute values producted, right, separately. So absolute value hk, absolute value x of n minus k. Now, nice, we have this, and we already started with let x of n less equal m. So let's also include that. So k, h of k dot mx. It's a constant number, right? A constant number. So you can see that actually this will be now, if this guy is bounded, you can see if this is bounded, I can really end up with the general definition. This will be my. I mean, meaning the output is stable, or the system is stable in the bounded input, bounded output sense, BIBO sense, or BIBO, how you pronounce it, where here my is really mx times the sum hk, right? Yeah, hk should be, I mean, absolute should be in there. So from here, you see definition for an LTI system, the stability definition of stability for LTI systems is, if I can say the system is stable, guys, LTI system is stable, or let's start with the if, or okay, it's same, stable if this absolute sum of the impulse response is finite. Sum k hk, it's called as absolute summability condition, okay? This is important for all k, of course. Okay? So I can, is this clear, by the way, this stability? It's an important property, right? We don't want to break the systems, like we don't want to blow up the algorithms. Similar thing for both physical systems, digital systems. When the input is bounded, meaning a finite number, a manageable number is sent in, the output should be finite. Okay? So let's look at now a few examples. Example, I'm asking you. I can give you the x of minus n. I can give you a few examples. Just a sec. Is the assistants here? Are the assistants here, guys?